Hello and welcome to Project 18 COVID-19 Reductions in Classroom. We are sponsored by Raytheon Technology. Our company liaison is John Jacobs. Our faculty advisor is Bob Dempster. Our team members are Andrea, Sebastian, Paul, and myself. Our agendas as follow: project objective, background and requirements, technical details, results and recommendation, and summary. Project objective and background. The project objective, the purpose of this project is to design a system that reduces the COVID-19 virus density to a safer level for students. Requirements. The project requirements are to significantly reduce SARS-CoV-2 particles in the area of a standard classroom area of 1,000 square feet with a ceiling height of 9 feet. Another requirement is to remove SARS-CoV-2 particles in the classroom with an occupancy defined by the current state regulation. COVID-19 background and transmission. The coronavirus disease 2019 is caused by severe acute respiratory syndrome coronavirus 2. This disease can be transmitted from person to person by means of droplets, aerosols, and fomites. Droplets are greater to 5 to 10 micrometers in diameter. Aerosols are less than or equal to 5 micrometers in diameter. Fomites is a virus contaminated surface caused through droplets. The following slides show an example of this. As you can see, the pink person is talking to the orange person, which creates droplets from the pink person's mouth. From there, the droplets can be carried on by air, which creates an airborne route, where the yellow person is likely to get contaminated. The droplets can also be too heavy to be carried, which results in droplets falling onto surfaces, which creates a fomite route, where the surface is contaminated. Anyone that touches the surface can be contaminated as well. COVID-19 background transmission. Although droplets, aerosols, and fomites are all confirmed forms of transmission for COVID-19, a large proportion of the spread is occurring through aerosol produced by asymptomatic individuals. SARS-CoV-2 particles have been found to remain as infectious aerosols in confined indoor spaces for many hours, up to 72 hours in closed rooms. The dangerous characteristics of SARS-CoV-2 is its ability to remain infectious in aerosol form. There are several important environmental factors that must be considered when dealing with the viability of airborne viruses: temperature, humidity, radiation, or UV index. Now I'll pass it to Paul to talk about technical details.
Thank you, Isidro. So infection is caused by the transmission of droplets or aerosols from an infectious individual onto the respiratory tract, where larger droplets will usually cause less severe infections, but smaller droplets or aerosols can penetrate further into the lower respiratory tract and cause severe infection. The probability of infection is dependent on the infectious dose or viral load, which is the point where infection occurs. The infection dose for COVID-19 is estimated to be about 1,000 virons. Some key values to look at to minimize the risks of infection in the classroom are the generation of virons by the infected individuals and the ventilation rate of the room. With this, we can find the expected concentration of virons in the air. Below is a table with examples of various activities and their contribution to the generation of airborne saliva. So next slide, please. So the ventilation rate depends on the number of air exchange per minute and the volume of the room. Knowing these values, we can then calculate the time in minutes required to reduce the viral concentration in the room, where C2 will be the desired lower concentration and C1 the generation of virons. The exposure dose over time can then be found to determine the probability of infection at this viral concentration. By using the graph, you could see the relationship of how cumulative dose contributes to infection. Ideally, you will want to keep this value under 60%, which is when infection becomes likely. Next slide, please. Since CO2 is exhaled with aerosols containing viral particles, we can associate elevated CO2 levels with increased probability of COVID-19 infection. A good way to monitor this is by looking at the room's ventilation, which is the amount of air changes per hour, or ACH. ACH determines how well the room is ventilated. For example, a room with high ACH, such as 5 or more, will have a lower CO2 concentration. So this can be used to monitor air purity. Next slide, please. Poor ventilation can be associated with higher risks for airborne transmission. From the data in figure 3, we can observe how our CO2 levels have a closely linear relationship to viral concentration, where C2 equates to higher viral particles in the air. We can see how our ventilation contributes to these values, where a classroom with high air exchange had lower CO2 concentration and thus lower viral particles were present. Knowing this, CO2 monitoring is a vital tool to measure the probability of COVID-19 transmission. Next slide, please. We also looked at the viability of the virus based on certain environmental parameters. Microorganisms, particularly in aerosols, are heavily affected by their surrounding environment. These key factors include sunlight exposure, or the ultraviolet index, temperature, and humidity. When these parameters are increased, the survivability or half-life of the virus is lowered. An interesting point is that ultraviolet light plays a big role in reducing the survivability of the virus. Shown on the table are UV index ranges from 0 to 10, but we are only focusing on levels 2 or lower, since we are estimating the lowest amount of sunlight exposure in the classroom. To better understand this, how this affects the virus's life in aerosolized form, we have some tables with data from the Department of Homeland Security on the next slide. So here are two tables highlighting the best and worst case times under different environmental scenarios for the half-life of the virus and illustrating how long it can survive under each condition. The left showing times for a room without sunlight, and on the right, the room with some sunlight at a UV index of 2. The highlighted squares on both tables show the times where in red is the longest or worst, and green being the shortest or ideal time. This helps us in monitoring virus spills and how long it can take to safely re-enter the room. It's important to note the difference in time the virus can survive in a room with sunlight versus none. And this shows us that by allowing some sunlight into a room, it can decrease its half-life by up to 85%, which is a significant drop in viability, which one should consider since it can be easily implemented. Next slide, please. Considering the effects of UV exposure, we performed a tray table analysis on 2 different methods of ultraviolet germicidal irradiation: upper air UVC and far UVC. UVC is used to inactivate the virus by damaging its DNA to kill or prevent it from multiplying and causing infection. Upper air UVC is a method of UVGI, which is directed at the upper portion of the room and is dependent on air cycling by the room's HVAC system. Upper air UVC is the suggested choice for this project, despite far UVC having more desired attributes. And although far UVC is more flexible in its application, upper air UVC is more readily available and has a history of safety and usage in hospital settings and works together with HVAC systems, which improve its efficacy in lowering infection rates in the room. Now handing off to Sebastian to further go over our trade analyses.
Thank you, Paul. Okay, so now we're going to take a look at a trade analysis done on portable air purifiers. So a portable air purifier is usually a standalone system that's able to provide filtration aside from the existing HVAC system. When choosing a purifier, one of the most important qualities is the clean air delivery rate, or the CADR rating. This is the amount of filtered air that the purifier can deliver into a room. This CADR rating is calculated with the known air changes per hour and the volume of the room. Generally speaking, a purifier should have a CADR rating that's at least 2/3 the size the area of a room. So for example, using the table for reference, if we have a room that's roughly 15 square feet, then 2/3 of that would be 10, which is the recommended CADR rating. And so for our project classroom of 1,000 square feet, our recommended CADR rating would be 600. Next slide, please. Continue with the previous topic. Here we have a tray table consisting of 3 different air purifiers. Listed from top to bottoms, we have the Air Doctor, the EnviroCleanse, and the Co-Way Air Purifier. Our determining criteria for each purifier were the type of filter used, the capable coverage of filtration, the filter size, and whether or not it had a UV light. So all of these purifiers were great in terms of having capable filters of capturing even the smallest viral particles. And in terms of coverage, each purifier was more than capable of providing acceptable CATR ratings. However, the deal breaker for us came to be whether or not there was a UV light built into the purifier. This UV light provides the added capability of not only capturing the virus in the filter, but also neutralizing it when it's trapped. The only purifier that had this added feature was the EnviroCleanse Air Purifier, and thus this ended up being our most obvious choice and recommendation as far as air purifiers. Next slide, please. Moving on, here we conducted a trade analysis on filters present in HVAC systems and air purifiers. The American Society of Heat, Refrigerating, and Air Conditioning Engineers, or ASHRAE, used this table to determine the effectiveness of a filter. Each filter is rated based on their MERV, or minimum efficiency reporting value. This scale ranges from 1 to 20, 1 being the lowest and 20 being the highest. Generally speaking, the higher you go up the MERV scale, the smaller the particles you're able to filter out and with higher efficiency. Based on this table, we can observe that the absolute minimum MERV rating needed to filter out the viruses is 13. This rating can be applied to either high efficiency particulate air filters or ultra low particulate filters, which we will discuss in the next slide. So here we have a simple tray table showing the differences between the 2 most common types of filters, HEPA and OPA. The determining criteria we have here were the efficiency of the filter, the smallest particle filtered, the MERV rating, and the cost. Each of these filters are more than capable of doing the job of filtering viruses with very high efficiencies, but the HEPA filters are the best possible option because they are much more economical than the OPA filters. Not only do the OPA filters cost more due to manufacturing, when installed, due to their extremely high efficiency, they have a very high airflow resistance. This will require the HVAC system or purifier to run their fans at a higher speed, requiring more energy and thus an even higher operating cost. So in order to maintain cost efficiency, the HEPA filter is the clear winner here. Next slide, please. With HVAC systems in mind, ASHRAE and the CDC have also provided recommended parameters for these systems to reduce the risk of infection. These recommendations are as follows: having filters with MERV ratings no less than 13, maintaining a temperature between 70 to 75 degrees Fahrenheit, and keeping the relative humidity between 40 to 60%. This concludes the technical details portions of our presentation. So now we'll transition into the results and recommendations. Okay, we begin this section by introducing the classroom configurations and dimensions used for conducting our simulations. In Figure 5, we have a pre-pandemic classroom layout of a typical Salazar Hall classroom. This classroom has an area of roughly 1,000 square feet and a max occupancy of 47 students. We use this table as our base configuration, for which we designed our 2 new proposed pandemic era arrangements on the following slide. So I will now pass it on to Adriana to continue.
Thank you, Sebastian. So for our pandemic era classroom configurations, the dimensions stay the same. For our configuration A, it uses a hex seating arrangement, so it kind of looks like a honeycomb. And this allows for a 6-foot radius between each student. The occupancy allows for 14 students and 1 instructor. Configuration B uses a more traditional grid seating arrangement that allows students to be 7 feet apart from the other students. The total students for this configuration are 12 students and 1 instructor. For the airflow simulations, we used the SOLIDWORKS flow simulation module in SOLIDWORKS. We were able to observe the local mean age of air, or LMA. The LMA helps us evaluate the fresh air distribution inside the classroom, which is important as SARS-CoV-2 particles are present in conjunction with CO2 particles. The better the ventilation, the less concentration of virus particles will be present. The parameters that we used for the modeling were temperature set at 72 degrees Fahrenheit at 60% relative humidity. This is our SOLIDWORKS model for configuration A. Here we can see the new air coming out of the inlets, and that is characterized by the blue arrows. As we see the air movement, we see the change in time for the LMA. The red means that this is the oldest air circulating in the classroom. This seating arrangement shows minimal red clusters, showing us that it's an effective configuration in allowing the room to ventilate. For configuration B, we ran the same simulation. And once more, the clean air is characterized by the blue arrows coming out of the inlets with the red air going into the outlets. A cluster of red arrows here raise concern as it shows air is stagnant and not mixing, which means that the air is not being filtered out, potentially keeping SARS-CoV-2 particles inside the classroom. And we can see that over here with all the red in the model. Our classroom-specific recommendations are to install an inexpensive real-time CO2 monitoring device to determine indoor CO2 levels and ensure that suitable ventilation rates are being met. The installation of UVC lights in classrooms, such as upper Air Uvc fixtures, to help reduce the infection rate from airborne pathogens such as COVID-19 and other viruses. The use of the hexagonal configuration, as it allows for better air ventilation inside a classroom. If that hexagonal configuration is not possible, then the use of a portable HEPA filter in locations where the air is stagnant in order to enhance the airflow and create better ventilation. Also, the sanitizing of high-touch areas throughout the day. General COVID recommendations. So we have certain guidelines and recommendations that will potentially help limit the probability of infection and improve the safety of staff and students. And these include the use of face masks, and they should be required to be worn while on campus, as well as having a standardized guideline that would establish what is an acceptable type of mask that, when worn properly, offers the adequate protection. Testing for COVID-19 should be requested for students and staff returning to campus with negative results at most 2 weeks before returning. Also, having staff and students perform a health questionnaire before arriving to campus would also help curb the outbreaks, as it would help keep students and staff that are showing symptoms of COVID-19 at home. Quick methods of COVID-19 testing should be made available and encouraged for students and staff to limit the outbreak occurrence. As well as proper personal hygiene should be encouraged, such as having sanitizing wipes and hand sanitizing stations readily available. Campus should also require staff and students to get vaccinated before returning to school. Now we're going into our summary for this project. Summary of what has been accomplished this year. The team studied the many forms of transmission for COVID-19 and how the virus is affected by its surrounding environment. We conducted trade studies, including those of UVC lights, filters, and portable air purifiers. We also created 2 possible socially distanced classroom configurations for a Cal State LA Salazar Hall classroom and conducted SOLIDWORKS modeling to determine the airflow for each configuration. We provided classroom-specific general recommendations to curb the spread of COVID-19 in the classroom. Future tasks that will make this design viable for the classroom are to perform tests using real-life data to record how effective each classroom configuration is, as well as conducting a cost analysis on the upgrades required to retrofit each classroom. Also, ensure faculty and students are vaccinated before returning to the classroom, and to continue enforcing CDC guidelines for the COVID-19 pandemic. Thank you for your time.